So we start. Let me say a few words to to introduce Professor Ian Garrick-Bethell, right? Your last name, your very last name, Patel.
Yeah, exactly. Yeah.
So today we have a first talk in the morning. Today we have 3 talks in this series. In fact, all on the morning, of course. The first talk will be given by Professor Ian Garrick-Bethell of UC Santa Cruz. The title is Surface Effects of the Moon, Past and Present Magnetic Fields. And he is an expert on this. And he got his PhD from MIT. And I think he did a lot of work already there, on the mathematics and paramagnetism. And that's where I tracked him down to it. But he's very interesting. He does a number of simulation, right? I mean, he's very, I would say, should I say that? You're very talented. Since it's not a secret, right?
Yeah.
And he also worked in the lab, doing instrumentation. So and he's very young. So we look forward to his many more important achievements in future. So yeah, please start your talk.
Okay, yeah, thank you very much for the introduction, and thank you for inviting me to talk with you. And you can see the mouse, I assume, right?
Yeah.
Okay. So yeah, the title of the talk changed a little bit to discuss what the ancient magnetic field on the moon and even the present magnetic field on the moon, how are those different magnetic fields affecting surface processes on the moon? Some of those surface processes were billions of years ago, and some of those surface processes are continuing today and in the last few million years. And these cartoons here show you the magnetic field generation on the moon billions of years ago in the tiny little core of the moon. And then today we see the record that's left of that era. We can see these little magnetic anomalies, and we'll talk about some of those. So the talk is in 2 parts. So I'm going to talk about the past magnetic field and the present magnetic field, and again, how each of those different types of magnetic field has influenced the surface composition. So I wasn't sure of the audience about exactly, what kind of background, if it's undergraduate or graduate or faculty. So I'll talk a little bit about.
They're mostly, I think, grad students. So I mean.
Okay. So yeah, the past magnetic fields, we believe the moon once possessed a global dynamo field. So that was what I just showed you. And this is just kind of going over it again. And then the present magnetic fields, this is a map from about 30 kilometers altitude of magnetic anomalies on the moon. You can see this is the rock has actually been magnetized here in different areas. And this magnetization in the rock will be stable for billions of years in the future. So I think I want to give a little bit of an introduction about dynamos in the solar system. So the science of magnetism is a very classic problem in geophysics, and it is hundreds of years old. I mean, obviously people were navigating even with the magnetic fields of the Earth, but magnetic fields are everywhere in the solar system, everywhere in the universe. These objects here all have magnetic fields, and it's pretty diverse how they manifest their magnetic fields. So the gas and ice giants. And there's dynamos. You can also focus on these magnetic fields that come from the terrestrial bodies. And the word dynamo applies to the process that generates the magnetic field in the core of these objects. So you can see some objects here, terrestrial bodies. We have Earth, and Ganymede actually has a dynamo magnetic field, is the moon of Jupiter, and Mercury. So again, dynamos common in the terrestrial bodies. And also on Mars, we believe there was a past dynamo, but there isn't one today. And you see that in the record of the spacecraft observed magnetic field in the crust rocks of Mars. And we have tons of meteorites in our collection, and we have been studying them in the laboratory, and we have inferred that asteroids once had dynamos. And that's pretty surprising to people in some ways, because these things, did not really have the conditions for very long to have a dynamo, but it turns out that they did. And the moon has been controversial for a very long time, and there's been a lot of work in the last 20 years and in laboratory measurements to figure out if the moon had a magnetic field. And I'll talk a little bit about that. So just a quick review of dynamo generation. I like to point out that they figured out quantum mechanics. So we figured out how quantum mechanics works before we figured out how the dynamo works. The dynamo is so complicated. It's a very complicated process. And it really, you can argue that it certainly still has not been perfectly modeled, but really wasn't until 20 years ago that we were able to illustrate some of its critical behaviors. Anyway, what do you need to have a dynamo? You need a liquid outer core and has to be an electrical conductor. And could the moon have ever generated a dynamo? Did it ever have these conditions, a heat source that had this liquid outer core to be convecting and undergo complex motions, and it needs to be made of iron? And so back in the 1950s, people had the same question. Did the moon have a dynamo? That was, and these are the first spacecraft that ever left the Earth, the Luna 1 and Luna 2 missions in 1959. These spacecraft were sent by the Soviet Union. They had no cameras with them, but they had magnetometers with them. So I find that to be a very a nice illustration of the importance of magnetism in the history of geophysics. And they found that there was no dynamo field on the moon. That they had the dipole field, the main part of the field, was 10,000 times weaker than the Earth. So essentially there was no global dynamo on the moon. But then the Apollo program found that with these little tiny, relatively small satellites that they released from the Apollo 15 and 16 satellites, they made measurements of the magnetic field. And there was no dynamo globally today. There's no global magnetic field, but they did find these little blobs of rock that were magnetized, and they produced maps that show the concentrations of magnetism in the crust. And just to review what you're looking at in that map. So this is it's kind of old now, this map, but this is a map showing you that the magnetic field here, 170 degrees longitude, is 12 nanoteslas, those are units. And how did that happen? How did the rock in the surface get magnetized? So what happened was you had a global magnetic field billions of years ago, and here you have some rock, and it was cooling, so it was above the Curie temperature, which is the temperature at which things become ferromagnetic. And it's cooling down, and it will record this global magnetic field so that even when the field is gone, the rock will retain a magnetization vector here. So the field disappears, but the rock remains magnetized, and it creates this field that we can measure with a spacecraft today. So that's what you are seeing in the crust of the moon today. Those are the present magnetic fields that the moon has. And so the present magnetic field map, there's a couple versions of this map now. Kaguya Data produced another iteration of this map, near side, far side, and you can see these little blobs here and there, and they are really quite interesting. And they're and I'll talk a lot more about Reiner Gamma shortly, but they give you clues about the dynamo behavior in the past, but also we'll see space weathering. They give us a lot of clues about how space weathering works on the moon. And I want to emphasize, okay, so there was a paper that came out a couple months ago, maybe nobody noticed it, but it argued that there was never a dynamo on the moon. And so I want to, make the case that there's been a lot of work showing that there has been a dynamo on the moon. It's people are still debating some of the details of it, but there's lots of evidence that there was a dynamo just from these types of maps. And also we're going to make more measurements. August of next year, Korea will be launching their first mission, and that has a magnetometer on it. And if we can get really low, for example, on some of these anomalies, that would be quite useful. So the other way feel free to interrupt me if you have a question, of course. So the other way we know that there is a magnetic field on the moon in the past was through just looking at rocks. So all the Apollo samples we brought back. And you can see a chart here of the time before present. And over here, you can see how strong we think the field was. So about between 4 and 3 billion years ago, we think there was a dynamo based on these really strong fields. So in case you didn't know it, the Earth's field is somewhere around here. So these are intermediate between, these are like almost Earth strength fields. And so it's pretty hard to explain how these rocks got so magnetized. You need a dynamo. That's what we think happened. So we're pretty sure there was a dynamo at some point, although the details are debated. And so why are they debated? I mean, the thing is, no one thought the moon could have a dynamo. The core was believed to be, people didn't even think it had a core. People initially, like the Soviet Union, they were curious about it, but people did not expect the moon to even have a core. People thought the moon was a giant meteorite. It wasn't until the Apollo program that became evidence for a core, and then evidence for an ancient dynamo in the past. But I do want to point out this paper that came out in August recently that showed in Science Advances. It got some, it was popular in the press even, so some reporters talked about it. And they're saying there was not even a dynamo on the moon. And so there is still controversy, there's still debate, which makes it interesting for us to talk about. But I would argue there is strong evidence for a dynamo existing on the moon. And the question I want to ask today is, how did that dynamo interact with the solar wind in the past? So basically, here's your Earth, there's the Earth in the solar wind, and you can see the question is like, what kind of interaction was happening a long time ago when the moon had a magnetosphere? Was it blocking the solar wind from accessing the surface? And why do we care about that? Here's some reasons why that might have been important if the moon had this global dynamo field. The first one is that hydrogen ions are important for producing, potentially important for making water on the surface. So you take H+, you combine it with the oxygen in the soil, and you can make water and put water everywhere on the moon. And the other thing is that there is there's some classic studies of the isotopes of the sun in the solar wind. And so the Apollo astronauts brought back soils from the moon that were billions of years old. And that let them study the composition of the ancient sun, because they could measure things like helium and nitrogen, or actually nitrogen's a little harder, but yeah, helium, argon, different gases that were in the soils. And they were able to estimate the composition of the sun. And we'd also be curious maybe if there was weathering of those ancient soils. But that one's not as well studied, I would say. So I'm going to focus on this question of, how did any solar wind isotopes get through the magnetic field in the past? And can we learn anything about how water was created in the past? And can we learn anything about the ancient composition of the sun? Because, like I said, the Apollo astronauts, they brought back these ancient soils, and they found these ancient solar wind species in the soil. But how is that possible if there was a magnetic field that could be blocking the solar wind? So these are the kinds of things I want to investigate: hydrogen and water creation in the past, and the implantation of isotopes in the soil. And so there is a body of literature that has looked at these old lunar samples that are billions of years old, these old soils and these young soils, and they have shown that the ratios of certain isotopes in the solar wind have changed in time. And so you can see here old samples, young samples, and these different solar wind isotopes have changed. And people have debated this for decades to see whether it means that the sun's isotopic composition has been changing over billions of years. And so it's something important for solar science. And so what we realized, my idea was that these ratios that are important for the solar science, which have changed maybe based on the samples, if there was a magnetic field, it's possible that the heavy isotopes can penetrate the magnetosphere more deeply. And so you could have different ratio changes of the isotopes created by an ancient magnetosphere. And so we call it like a fractionation, or to change the fraction of the different heavy and light isotopes from the magnetosphere. So that was one hypothesis that we wanted to investigate. And the second one was, a long time ago, did the water process change at all based on the magnetic field? And so today, here's a map. This is a map from the present day of the water on the surface of the moon. Maybe some of the other people have given talks on this, and so you've seen some of these maps, that the water is this thin layer of water, or OH, kind of at mid latitudes on the moon. And there is an idea that some of this water eventually can, migrate around to the poles. And the idea is also that this water you're seeing here is actually from the solar wind as the H plus combines with the oxygen in the soil. And so we're making water every day on the moon. And, this is something that we still don't understand and is being studied right now by the Chandrayaan-2 spacecraft, in fact. So it's still evolving science. But there is an idea that all of that water eventually makes it to the polar regions over billions and billions of years. And so this is a map now from 2011 that shows evidence for water ice on the poles of the moon. We don't know about how this ice got here. We don't know if it is ice. I mean, there's some good evidence it might be ice, but we really don't understand where it came from. And so there could be a connection over billions of years to the sun producing some of this water. And the other question then is, is there, if the magnetic field existed for billions of years, you would block the creation of the OH and you could maybe block the polar migration process. And so this was just we never asked this question before. So we wanted to do some simulations to answer these questions. Okay, so we used to do these types of simulations. These simulations actually were done at Berkeley with my colleague, Andrew Poppy. You may know him. I've worked with him for a number of years, and he's great if you have a chance to meet him. And so we wanted to simulate this so-called paleomagnetosphere for the first time. And we wanted to ask those questions. And we used this thing called a hybrid plasma model. And the hybrid plasma model makes some approximations to keep things stable numerically and to be practical. And so it treats the ion and electron motion differently. It treats the ions as discrete particles that it can track, but it treats the electrons as a fluid. And the reason for that is that the electrons are more pushed around adiabatically by the magnetic field, but the ions are less adiabatic, and maybe you want to treat those as discrete particles. And so the hybrid plasma code has proven useful in these types of problems. And so the problem that we face, though, how strong was the field in the past? And also, what was the solar wind like a long time ago, billions of years ago, on the moon? So those were other parameters that we needed to put in. And again, yeah, feel free to interrupt if you have any questions. So, okay, so the next part of this was how strong was the field? And so I showed you this map earlier.
I want to ask you a question here because you showed us the diagram before. Look here, yes. The magnetic field strength. I noticed that it dropped away drastically at about 1.5 billion years ago. Yeah, is that real? I mean, is that estimation?
Yeah, well, there's the rocks in the last billion or so years have no evidence for a recordable field. Like they have rocks that should have, the rocks that we have from a billion years ago can record fields, but they don't. There is no record recently of a magnetic field more recently. So this is like the period, like these are good, these are nice rocks. They if there was a field, they would have recorded that field, but they didn't. There's really there's no magnetic record here.
But then so you have 1, 2, 3, and from today you have 1 point, right? And then you have 1, 5, 1, 5, 4, 8, 4, 6, 5, and 5, 0, 1, 5, and then you have after that one you have another one. Here, that one, is that real? I mean, this the blue, the one, the data point with blue color. Yes,
this one.
Yeah, right.
Yeah. This one, the age of this rock is really badly known. So I think I agree with that there was a field, but I think that the error, it could be even worse than this as far as
the age diminution.
Age, yeah. So the x-axis here is like highly uncertain. So I don't think you can connect this to this region with confidence. I don't think we know what it looked like in here very much.
Good.
It's very unknown here. I think there's very little data in here.
Yeah, thanks.
I wouldn't trust the this X bar very much. So yeah. Does that help your question?
Yeah. The answer.
Okay. Okay. Anyone else? All right. So we had to figure out, how strong we want to make the field, and we basically chose low values of the field. It actually gets harder to use a hybrid code for the higher values, but we thought 5 microtesla would be a reasonable maximum. And it turns out we see very strong magnetosphere effects at 5 anyway. So, and we also limited, we wanted to, we don't want to be too recent because the solar wind has different behavior here in the past. So that's the next part. But anyway, we go up to 5 microtesla, which is, kind of within the range of rocks you can see here. It gets very strong, but we don't need to go so strong to make a magnetosphere. And then, so the other question is, how strong was the solar wind? What was the density of the solar wind, its speed? What was the interplanetary magnetic field at the time that was frozen into the solar wind? And there's been some studies of other stars around us at different ages, and people have estimated the solar wind speed, density, pressures, and the interplanetary magnetic field. And we can make this kind of crude plot that shows the the solar wind, how it changes with time, with pressure, how its pressure changes, its density changes, and its speed changes. And so we use some of these values in our simulations to more realistically simulate the solar wind. Okay, so here's the first results from the code that our simulations. And you can see the 5 microtesla paleo intensity. And so that's the strongest simulation that we did. But you can see that there's a strong magnetosphere effect even at 2 microtesla. So this is a picture of the density of the solar wind. And this picture maybe is familiar to you. You've seen pictures of the Earth's magnetosphere. And so it looks very similar, similar cusp structures that are forming. And even down at actually half a microtesla. So it's a very weak field. You still get a very substantial magnetosphere. And at 5 microtesla, you certainly can see that here. And there's evidence even that there may have been, you can imagine there may have been radiation belts starting to form even at 5 microtesla. And then we also played with the field orientation. So this is for a dipole field pointing up in the page. And then you also have the case where the dipole is pointing along this axis here, as indicated by the arrow. And the problem is on the Earth, the spin axis is aligned with the dipole axis, right? Like the North Pole is close to the spin axis, right? And so, but that may not be true. Like there are scenarios where you can have the North Pole at the equator. The North Magnetic Pole can be at the equator, and that there's some evidence even that may have happened on the Earth, and it may have happened on the Moon. So we simulated both of these conditions, and you can see that you get a North Magnetic Pole here, and you have a cusp region. So I'll call these things cusps, and these cusps are important because that's where the plasma can get to the surface on the Moon. And so here's some a summary of how much solar wind used to reach the surface of the Moon. And the pattern is pretty similar. You can see the flux here and the latitude. So at the equator, for these cases here with the North Pole aligned with the spin pole, you can see very little flux is getting to the equator. At 5 microtesla, it's really very little flux. So you would expect you should have no solar wind implantation, or very little at this field intensity. But the interesting thing is you actually have an increase in flux at the poles, and that's because of these cusps. And in this chart, you can see if you had no field at all, that would be this black line here. So that's kind of the no field. You turn the field on, you get these colored lines, the different colors. And you can see at the poles, you get a really big jump in the flux at the poles, at these channeled into these flux cusps here. So that was not that surprising, but no one had actually looked at any of these questions on the moon. And if you look at the global flux that's hitting the surface, this is the total amount of solar wind hitting the surface as a function of the field strength. You have this early on, you get the entire planet or the entire moon is shielded. But then eventually the funny thing happens where actually the cusps start strongly channeling the solar wind into the polar regions. And so actually, you don't completely turn off the solar wind because of this cusp effect, and you can get some quite strong enhancements of the field of the plasma there. It's only really in this one area where you have almost no solar wind flux at all. And this is at 5 microtesla out here, where you have this increase. And presumably, I don't know where it stops. We didn't go any higher. So we conclude that a lot of flux is channeled to the poles. And we were interested in, again, the question was, how does this affect water? And so the problem is we don't know enough yet about how water forms on the moon. I think we will learn that soon. With the Viper rover mission that NASA is hoping to send to see what the nature is of the water at the poles. And also Chandrayaan-2 will tell us more about how the water forms in the solar wind. But I would say if the solar wind is important, this ancient magnetic field is turning off that process, but it's channeling a lot of water directly, a lot of hydrogen, directly into the poles. So if, that may be important as well, but I think, we still don't know enough about how water forms on the moon to interpret these results. And so this is kind of a first study of the magnetosphere. And the second result, you may remember I was telling you that old lunar samples and young lunar samples have different heavy and light isotope ratios for the solar wind. So these are really billion-year-old soils that have collected different isotopes from the solar wind. And our simulation results show you that depending on the field strength, you can change the ratio to match the old or the young. So this one, it's very confusing. You could do anything you want with the magnetic field, and it's a little bit worrisome. So if you're studying argon and krypton isotope ratios, the magnetic field can really mess up your studies. And so you do need to worry about the magnetic field on the moon a long time ago. This one has more of a consistent trend, is that the magnetic field at stronger and stronger values, maybe it approaches the old lunar value, the old samples. So it's possible that a strong magnetic field in the past may explain the isotope ratios in the sun for some old samples. Our code stopped becoming functional at these higher fields. And so we want to carry this to higher field values in the future. But right now, there's just some evidence maybe that this ratio is affected or explained by the moon's ancient magnetic field. So this was published recently, but still preliminary, and we want to continue these simulations to try to understand these ancient isotope ratios. These may not be a record of the sun's composition. These may be records of magnetic fields, and we see the early indication of that. We also need better constraints on the ancient strength of the field, and then that may come with more samples of the moon. Okay, so that's most of the first part. And the conclusions there are that, this was the first simulation of was there a chat here? Okay. Oh yeah, sorry. Nope, not for me. We believe, almost certainly the moon possessed a paleomagnetosphere, and even larger than Mercury's present day magnetosphere. It's pretty easy to get this effect even with low paleo intensities of the field. And we can change the surface of the flux greatly, and we can slow down the hydroxyl formation. We can change where we think maybe water is getting created. And we're going to need more measurements of waters on the pole, or we're going to need Chandrayaan-2 results to be fully analyzed to really interpret how this might affect things. And you can see some of our results here in our preliminary studies. in these papers. All right. So that's the past magnetic field and how that affected the moon. And again, if you have any questions, it's fine to interrupt.
Yeah, before you go on, Ian, I mean, the lunar dynamo might have something like the polar wandering, right? Like the
sure.
Earth. Yeah, so you can, I mean, the polar region could not be fixed. It could be just move around. Yeah.
Yeah, I think that's a really interesting question. I think the problem is we know so little about the moon's dynamo. And so, I think the problem is no one can explain, there's no theory that can generate a dynamo on the moon. It's a really big problem. Like all the evidence comes from samples and it comes from spacecraft, but the people that work on the computer and the theory behind the dynamo, they don't have any good theories. So we don't have a good model to simulate the dynamo on the moon. We can't explain it. It's too strong. So I think eventually, though, we will come up with the mechanism that produced the dynamo, and then we can ask questions like polar wander, or and try to model things like that. But we still have a lot of problems explaining the moon's dynamo. So.
And you just mentioned Mercury, and Mercury also has a water ice deposit at the polar regions. But then from neutron detector mapping, the idea is that for Mercury, the distribution of the water ice, at least the subsurface water ice, the thin layer, is very, how to say, very concentrated. On our hand, for the moon, is rather fragmented. On the moon, they could be just distributed in very small pieces, diffusively. And the idea is that because the moon might even have the inclination might have changed, in the past, rather, not. I don't know how frequent that is, but that was one of the explanation.
Okay, so now we're going to go to the present day and say, well, the magnetic fields on the moon today are also telling us something interesting about the solar-wind interaction. And I'm going to propose a really simple question, and it's, does the moon's color and brightness change with latitude? And why we think that might be the case? Because the sun today is hitting the moon, but if you go up to the poles right around here, you can see that the solar wind is just kind of barely hitting it. It's tangential to the surface. And so the flux of particles per square meter is very low. Now, the solar wind makes the surface dark, we think. So over here, you expect the moon to be darker. And over here, you expect it to be much brighter. And this was a theory that people have suggested or talked about, at least in the community, for decades. So the moon should be darker at the equator, but nobody had ever found the evidence that the moon is darker at the equator. Paul Lucy's tried in their data. There's a little bit of a discussion of this effect in Yokota et al. 2011 about some highland samples there, some highland regions. But no one had shown definitively that there's this global change in the color from the solar wind. And so one idea I had was to try to let the magnetic anomalies help us, because these magnetic anomalies, here it's called Reiner gamma, they have funny colors associated with them. So this is a map of the magnetic field. The contours are nanotesla. And you can also see the color is different here at this Reiner gamma swirl. And the idea, we think, is that this has been known for decades. And so that we believe the sun is being blocked. The solar wind likes to make the surface dark, but the solar wind is blocked by the magnetic field. And this is very small. This is much smaller than the planet. This is a mini magnetosphere. And you can see the soil is very bright here, we think, because maybe the solar wind can't get to the surface of this so-called mini magnetosphere. This is an old theory. So my idea was that the solar wind is reduced up here, but it's also reduced here. So can we check if the color is the same at high latitudes as at swirls? And so nobody had found the effect before. And so it's a very small effect. So I wanted to get the help the swirl, this swirl region where the field is blocked. And so I came up with, and my student and I came up with this new way to think about the colors of swirls. And so here's a picture of a swirl at one band at 750 nanometer reflectance. You can see it's very brightly colored. And the normal background soil is over here. And so then there's a funny way to look at the spectral data. And you can take the spectrum at 750 nanometers, and you can plot that with the ratio of the 950 nanometer to 750 nanometer reflectance. And people had noticed that there was this everywhere on the moon, that all these red pixels, all the red pixels here, make this nice trend. And there's a very nice slope with this. And that's because all the fresh little craters are very bright, and they're over here, and then all the old craters are over here, and you get this nice line, and that's the background. But I noticed that something funny and different happens with swirls. Swirls, you can see the yellow and the green and the blue, they move their trend over to the right. So they don't, everyone thought that the swirl would be over here maybe, but actually a whole new parallel trend develops in the swirl. And so my student and I, Hemingway, we quantified this trend. We call this the beta trend. And we called the background trend the alpha trend. And then we looked at other swirls to prove that this beta was actually consistent on the mare, the volcanic plains of the moon, at least. So you can see the background in the red is like this, and then the blue is like that over here. So you can see this is a consistent thing, this so-called beta trend. And that's present everywhere on mare swirls. And we quantify them based on the slope of the trend. Pretty straightforward, kind of, you can think of it as a coordinate transformation. But yeah, basically we call these the alpha trend and the beta trend. And there's some slopes associated with those M1 and M2. So that lets us separate out the colors of, or the different, the different colors of the swirl. And you can see now a map of the beta, the swirl trend. It emphasizes the swirl, and then the background trend, the alpha trend, emphasizes and shows all the little craters around here. So this was a nice way to separate out these two different swirl trends and background trends. Okay, so now let's just look at the latitude of the moon, different latitudes, and we'll do the same thing for different latitudes. We have the 750 nanometer reflectance, and we have this ratio here, and then we will plot the points everywhere at different latitudes, and we'll connect these different points for different latitudes. So the blue points are 60 degrees, and the red points are at the equator. And what this shows you is that as you get closer to the equator, these blue points, you're getting brighter, right? Here's the reflectance is going up, okay? And so this slope of this trend turns out is exactly the same as the slope, the beta slope for the swirls. So that was really exciting to us because it's the same physical process. The solar wind we think is creating the beta trend. The solar wind is being blocked at the swirl. And then at the same thing is happening here at different latitudes. The solar wind flux is decreasing. And so this spectral trend, we call it B here, the B trend matches the beta trend for swirls within the uncertainties of the slopes, the 1 sigma uncertainties. So we think, we call these statistically identical, at least. You can see them overlapping each other here in this chart. Okay, so then we were like, let's just make a map. Let's look at the picture of the beta value all the way on the mare. And you can see it has this nice, here's latitude and then beta. You can see it as this nice, consistent pattern here. And so the swirls are behaving just the same way as the entire lunar marea. The marea are getting the solar wind blocked, or they're not getting it blocked. There's just less flux. There's less solar wind at high latitudes per square meter. So that was a very exciting result. To no one had really noticed this before on the moon, that the color of the mare changes. But then we just said, oh, let's just look at the brightness. Why are we using this really complicated thing, beta and alpha? And it turned out we just looked at the brightness. And we looked at the brightness of the mare, and we had to be really careful about what is the mare, what is the background highlands. And so we had some special tricks to make sure we were just getting mare. And then you can also see the brightness with latitude. Here's latitude and reflectance. You can see the brightness is getting higher at the poles. And this is a different instrument here. This is the laser from LOLA, the laser lunar orbiter laser altimeter. And that also measures the reflectance. And this has no phase angle dependence. So that's what's nice about this, because at the poles, you get close to the poles and the phase angles get really weird. And so what's nice about this is there's no phase angle dependence, because the instrument is always looking down normal to the surface. And you can see that. So we have shown that the color of the moon changes with latitude. The brightness changes with latitude on the mare. And nobody had found this before because they were looking at the whole moon. And it turns out if you had just restricted your analysis to the mare, the signal is way nicer. And you can see this clearly on the mare. And then since our paper, then other folks have found the same thing in Lemelin et al. 2016, very nice study of the albedo of the moon versus latitude. And you can see at the high latitudes, you start to go up and get this little bit of extra brightness. And here's a couple other papers. There's a nice study as well of crater walls in the Earth's magnetosphere and outside the magnetosphere. Anyway, so it looks like the evidence for that was confirmed eventually. And so that was a nice linkage between, solar wind is controlling the color of the moon. And we also were able to use, these swirls to prove that a little bit more thoroughly and show that the processes operating towards high latitudes are similar to these solar wind blocking processes that are happening at swirl. So there's a nice connection there. Now, we don't know how much solar wind is being blocked. Like here, we know we can do the math. It's like a cosine function. Eventually here, it's 0, and here it's 1. It's the exact amount. But, we don't have we can't really know what's going on in swirls yet. We still don't know the energy of the particles hitting the surface. We don't know the flux. Is the flux the same, but the energy is different maybe? So there's a lot of questions still about how much the flux and energy are getting changed at these regions. But I think that it shows you that these regions are really nice laboratories to study space weathering and understand these global patterns on the moon. And also you can apply that all to other airless bodies like asteroids. And then I think I'll just end with this final thing, that if you have a pair of binoculars, you can actually, with your eye, you can see this mare here in the northern part of the moon. And you can see it's not dark. It's bright. And nobody previously realized or appreciated that this is part of the reason, not all of it, but part of the reason this is bright is because it's so high north and there's not enough solar wind flux up there to make it dark. So that is the end, and I can take any other questions.
Yeah, thank you so much. Any questions from the audience now? I think it was the Garrick-Bethell, very, I would say, rather comprehensive, not very detailed, but comprehensive enough, to tell you, to give a taste of the. Basically, it's a heavy ions, interacting with the magnetic field, lunar magnetic field, and some of the possible.
I wasn't sure how much detail you guys wanted, so I don't know. Yeah, I didn't know what the appropriate amount was. So hopefully that was okay.
Well, you could give another talk,
Okay, yeah.
Fiona has a question. He asked about why this. You're talking about the argon xenon ratio. At the beginning you mentioned that. So
yeah,
we want to ask you about that too. Yeah, right. There was I think the previous diagram. The one here, right? The one. I think.
Yeah.
Mhm.
What was was a specific question?
Right. Why you? I think you asked that. Why is it interesting, the ratio? And the next question, of course. Why is time dependent? Yeah.
Yeah. So that it gets into how the sun is burning its fuel sources. So it's really a question of solar science, and like if you there's I think my understanding is, and this is not my field of expertise, but if the solar theorists, the people that study how the sun operates, this should not change in time. Between 4 billion years ago and today, there should be no change in these ratios. But if there is a change, then the theory for how the sun is burning its elements and producing these isotopes, they need to make some changes to the theory. So
you have a straight line there. At what time is that straight line indicating?
The time between these old and young, the reason we call them old and young is because the ages are not that well established. We know that some of these are up to 4 billion years old. I might have a backup slide on this, actually. See if so let's see how old some of these are 3 billion years old, and then the other ones go down to like 0.1 billion years old. This one actually, it looks like they're closer to 4 billion. But the way they estimate the age for soils is really bad. Like they have to actually use argon isotopes in the soil. So it's quite complicated, and we don't really trust these ages very much. So we just say old and young. Something like 2.8 is old, and this one is young. But yeah, it's more the science question is how does the sun operate, and that's why it's a puzzle. If this is real, then it may tell us something about how the sun was operating. But I think it could just be, we could explain this potentially through these isotope weights in the magnetosphere.
So that means, Fiona, Professor Garrick-Bethell is going to tell you that the other explanation, more likely, maybe more possible explanation, right? Using the magnetic field.
Yeah, I think the problem is, it's like, as you can see from these results, I think the problem is we don't know enough about the field. We don't know about its orientation, because if the field can do this, then there's, the ions will come right in through here. And so there'll be no change in the different ratios of different masses. Maybe it's just the problems are too complicated right now. We need more background information about the dynamo. But I think it shows that there can be a strong effect on the isotope fractions. Okay, I think, as you can see here, you cannot trust these ratios now, because we can show you that the magnetic field can create any ratio you want.
And then the difference in the ratios partly because of the finite gyro radii.
Exactly. Yeah. Right. Yep. Yeah. Yeah. Actually, it gets a little complicated because the charge is also changed. So it's not just, it's the charge to mass ratio. And if you're interested, we show in our paper the charge to mass ratios that we use.
The one question I always have is that about the space weathering rate,
sure.
The time scale. You have some? Can you tell us honestly some good numbers?
Yeah, it's there's some studies from asteroids where people can say that solar wind is like on the order of less than 100 million years. So people usually say that the solar wind is doing the weathering on like millions of year timescales, but nobody really knows for sure what the actual number is. But it's fairly quick. It's not billions of years. It's something probably on the order of millions of years.
That's what we think. For 100 million years is even 10 million years is a interesting time scale, because the dynamical lifetime of I would say, near Earth asteroids, basically on the order, right?
Yeah.
However, more recently, just I think a few years ago, a couple of years ago, some Japanese scientists look at the samples brought back from Itokawa.
Yep.
And they claim that the space weathering effect actually is much shorter, on the order of about few thousand years.
1,000 years. Okay, yeah.
This is unbelievable to me, But I think you what. So I just want to ask your opinion.
Yeah, I mean that's also different because I mean it depends. Also, some of those weathering products are like sulfur and carbon. I mean, it depends on the type of asteroid as well. But yeah, I've never said anything. I always just say millions of years because I think we don't really know for the moon. So.
Because for asteroids, you know that for the S-type asteroids, they have another class of asteroid called Q-type.
Okay.
They basically are originally the same composition. So that in the main belt asteroid, which is outside the orbit of Mars, we find very small number of Q-type. They're almost non-existent.
Okay.
Because the idea is that when originally you have a new fresh asteroid surface, they would be as a Q-type spectra, but with space weathering, then it becoming S-type. Yeah. But
so
then
they're young.
Yeah, and then so presumably in the main belt, the asteroids are basically old one. But once you get into for the near Earth asteroids, they would be how to say their orbit would be destabilized because the planetary scattering. As a consequence, that also that they will have a higher frequency of close encounter with terrestrial planets.
Yeah, the tidal disturbance. Yeah.
Right. So the idea is that then you look back the time scale of planetary encounter, and they tend to be on about million years, that kind of thing. Yeah.
Yeah.
So we always thought that is a nice explanation, a comfortable explanation, until the new idea from the Itokawa sample return come up. So either that number, the very short time scale is wrong, but and I hope
go ahead.
No. I hope that you will say yes, it's wrong.
Yeah, I mean, there's no good studies in the laboratory to simulate this. I mean, because the problem is the flux of the solar wind is so low. I mean, and you'd have to, how do you simulate that in the laboratory accurately, and simulate the movement of the regolith from micrometeoroids? Like, it's a horribly complicated equation, I think, that describes the equilibrium color of a soil. Like, why doesn't it reach saturation? Like at the poles, I mean, I don't understand this. Like, why, you have these mare are 3 billion years old, around 3 to 4 billion years old. You would think that they would saturate after a while and everything would become dark, but it's not the case. I mean, there's some equilibrium part of this equation that's keeping the soil bright with time. And that's probably the effect of micrometeoroids that make the soil brighter with time. So there's a competition between different rates to give you the equilibrium. So, and even, just in the last 5 years, people have changed the micrometeoroid weathering rate by an order of magnitude. So I don't think we really know, but yeah, I don't know, hundreds of thousands to millions of years is kind of what I would guess the solar wind weathering rate is going to be.
That you have already answered that there's a new question from Yahui. Can you just ask Ian, right?
Yeah, sure. So thanks for the talk. It's very cool. So I have a question regarding the alpha and beta trend. It's really cool.
Okay.
Yeah, especially the Monty Opens on the moon is kind of like a high altitude, about like 50 latitude, and then that has been proposed by the Cruz bedrock from the Indian Basin. So it's more complicated as it has it has the compositional difference and also the higher latitude. So I'm just wondering, have you thought about like using this technique to the other part of the moon portion, potentially like compositional like anomalies?
Yeah, I think it's an interesting question. Like I wanted to ask those questions. Like what does, especially, yeah, like if you have some really interesting feature at a high latitude, like how much, like, is your interpretation wrong now? Like what do we have to make some correction for latitude? And I think the answer is yes, but I never pursued. I stopped working on it around that time. But I think in some cases, yeah, you may have a different interpretation, particularly like olivine abundances. Olivine can be sensitive to space weathering effects. And so, yeah, I think it is. I don't know that, like, I don't have a definitive answer, but I think it can be important. I mean, I even like another question that's related is like the north and south facing walls, or the pole and equator facing walls of a mountain will have differences in their solar wind flux, and even like and the north and south walls of craters. I mean, these are all features that are facing into the solar wind with different angles, and so you could start to ask those questions. So I think it's a really good question, but I never pursued it beyond that. But yeah.
Oh no, you need like a student to work on that, to like start working on that. I think that would be a very cool project for like a student, like a graduate student.
Yeah, I mean, I think like if I go back, I think the closest related paper is like Sim et al. 2017. And this is, she looked at east and west crater wall differences. And so, and there's definitely an effect. I mean, and so it just depends on, it depends on the latitude. And this effect is it's quite interesting. This is one of the most interesting papers on space weathering, I think, Sim et al. So check that one out if you haven't already. It's about the east-west wall differences. And so, and she found that there's some differences. And so, I think.
Yeah, I haven't read that paper, but thanks for the reference. Thank you.
Okay, yeah.
The Korean mission, they have this camera which is with a polarization, polarimetric, photopolarimetric measurements. And the idea is that they want to see this, as you said, the solar wind impact effect on opposite side of the crater wall. Yeah.
Yeah, I think also I think a huge thing that's going to help in that study is, does grain size change with latitude? So I'm also an author on another paper that was published like 4 or 5 years ago on the polarization measured from the Earth. So it was a ground-based telescope that measured polarization on the near side, and they found that the grain size gets really big in the high latitudes. And because this picture right here, this picture applies to micrometeoroids too, right? I mean, like in the plane, if the micrometeoroids are concentrated in the ecliptic plane, like the micrometeoroid flux it's not as precise and as exact as the solar wind flux, but the micrometeoroid flux, if it's somewhat in the ecliptic, will get lower up here, and you should have less micrometeoroid weathering. So maybe everything that I've said here is wrong, and it turns out this is a micrometeoroid effect. So I think we're correct, because we use these swirls, and the swirls don't care about micrometeoroids; they just care about the solar wind. But it is true that there's going to be a little bit less micrometeoroids here, and they see that evidence for that in the grain size. The grains are bigger here, and the soil is bigger. And if they can show that from orbit, I think that will be nice, because I think the observations from the Earth are not perfect. And I can send you that paper too if you're interested. It's Jiang et al. Type it into the chat. I think it's 2016. Check the year. But yeah, that student, I'm a co-author on that paper, but they talk about the grain size dependence with latitude. So the polarization PolCam will help with that too.
You say this is Zhang Yang, right? Is that
Zhang Minsup, I think is his full name. It's like Min.
He's from Arizona, is it? He was a Mahucha student, was he?
No, he was a student in Korea.
Oh, okay, all right.
Yeah.
But then if you really talk about meteorite bombardment, that there should be also the leading side, trailing side symmetry, perhaps.
Sure, yeah. So all those effects, I've not seen them discuss. I haven't seen them thinking about grain size with the leading trailing effect, but they were that paper we considered the latitudinal dependence of grain size as to be due to micrometeoroid. So, but yeah, you're right. Yeah.
So any other person have questions to Ian?
Yeah. So let's see. Masaki asked another question. Nishino. Yeah. Okay. Yeah. Thank you for your question and your feedback. Thank you. So your question is how the fine and complicated magnetic anomalies were formed. So yeah, I've tried to model some of the structure there at some of these anomalies. And actually the Reiner gamma one is like this one looks like it's like a disc actually. And if you model it like a disc, a magnetized disc, you get those same cusp structures. And so in this one paper, if you're really curious, I'll type it in here. We look at we model the what we think is the we basically take a disc an elliptical disc and we magnetize it, and you get already you get a pretty complicated magnetic field structure. So it's possible that you can explain some of these things with some simple shapes, and we think maybe this is like an oblique impact that made an elliptical crater. So but I agree with you, to really figure this out, you need better measurements. The measurements we have are poor of the magnetic field. And you really, I know what you like to drill these things really. I mean, on Earth, you just drill this stuff and take it back to the lab. But yeah, so I agree with you. It would be better to have a sample return.
Okay, great.
Great, thank you.
Because any other questions? If not, and I will let Ian go. It's how late is it now in California?
Actually, I'm on the East Coast right now visiting with my family, so it's even later.
10 o'clock. Yeah, 10 o'clock.
Yeah.
Past 10.
Yep. Yeah,
so,
it's okay.
Yeah. So I appreciate very much. We'll see you next time.
Sure. Yeah, I'm happy to come back, and I can give you as much detail as you like. Yeah.
Yeah. Okay. Thank you. Good night.
Okay. Thanks, everybody. Okay.
Yeah. Thanks.
Bye-bye.